Thanks for the invitation to talk. My name is Stuart Selve from ConnectomX. So the company was founded fairly recently in 2018 by just the two of us here. This is my colleague Cheng, and there's a picture of him pretending to use a microscope. We're based in Oxford in the UK. We are in a shared office in this building here. We do stick out a little bit because the other tenants are administrative, and I think they get a little bit sick of our banging metal and sparking electronics all the time. So I just wanted to give a brief discussion about serial block face imaging and some innovations within it, particularly in the context of our microtome. And as we start, I'd like to make a quick comparison between serial block face imaging and serial sectioning, which most of you are already familiar with. In serial block face imaging, we are removing and discarding a small amount of material from the sample and imaging what remains.
Stu, you're blocking the
and oh, sorry. Okay, I'm just blocking part of the screen there. And by comparison, serial sectioning is removing thin layers and preserving those for later imaging. And of course, both methods have pros and cons. So I found this by chance recently when visiting the Natural History Museum in Oxford, and I took a photo of this. It's a serial grinding machine invented by William J. Solis in 1904. And this was actually used for fossils which were too delicate to extract from rock. And instead he designed this machine where a thin layer would be ground away and the remaining fossil would be either sketched or, in the case of very valuable fossils, would be photographed. And this destructive process would be repeated until the entire fossil had been ground away. And these would then be reconstructed from the photos or sketches by cutting and sticking layers of beeswax together. And this method is actually still used today, particularly when the fossil is not suitable for CT scan. And it's now much easier with off-the-shelf equipment. You can see here they've put it in a milling machine with a grinding disc. On to more recent times, the next advance in this area was in 1981, when Alan Kazarian and Steve Leeton at Woods Hole Marine Biological Laboratory patented and built the first serial block face microtome, which could go inside a scanning electron microscope. This had a Z resolution of a few hundred nanometers and was used at fairly high accelerating voltage, which meant that it had to rely on the sample being sputter coated and etched between each cut and image cycle. And the etching was to extract more resolution out of the limited Z steps. They later designed a different mechanism analogous to a wood plane in order to more reproducibly remove a thin layer from a sample. More recently, in 2004, Winfried Denk published a paper describing a similar type of microtome with much higher resolution movements and to be used under slightly different conditions. And this produced groundbreaking results, allowing the reconstruction of neurons, including synapses and synaptic vesicles, over a relatively large volume. This necessitated the use of a stronger double osmium staining procedure to allow imaging at lower accelerating voltages and therefore high resolution without the need to coat the sample between cuts. This Denkatome, as it's called, is still in use and has also been commercialized by Gatan as the 3-view. This brings us to the present day, where we have three main solutions for serial block face imaging, which I'm aware of. One of them is ours, the Katana, which you can see at the top right. That's sitting on a microscope stage. We also have the Volume Scope and Volume Scope 2 by Thermo Fisher, and as mentioned before, the 3-view from Gatan. Just a couple of images of our system in its native habitat. So this is a recent installation at Cambridge University, and you can see that our entire system is very unobtrusive. We just have a small laptop with a user interface, a control box, and a single flange with the microtome itself in the chamber. And for size, here's an image of the system on a test scan stage. The whole thing is just 56 millimeters tall, so it's quite small and portable. I'd like to talk a little bit about the development of such a device and the challenges. These kind of devices have a very unusual set of requirements, both of which are easily solved individually with off-the-shelf parts, but together they're in conflict. So these requirements are for single nanometer precision movement, and also to have a very high stiffness in both the Z direction and the cutting direction. And just to illustrate the problem, if you take a solid metal block, roughly the size of our microtome, and you press on it moderately with your finger, it will deform by a few tens of nanometers. And what we're trying to do is make a similar sized mechanism, which obviously can't be solid, which can position the sample to within around a nanometer precision and hold it there under varying loads from interaction between the sample and the knife. So you can imagine it's quite a difficult challenge, and you have to do a fairly careful design in such a way that mechanical deformations cancel out as well as thermal fluctuations. And with our device, we also have the added constraints that it should be lightweight and small, which make things even more tricky. So here are some images of some early development process of our diamond knife or diamond knife holder. You have to rely quite heavily on simulation, but the best rule of thumb when designing such a machine is to imagine that it's being built out of rubber. And in this way, you can build up a more intuitive understanding of how parts deform and which parts need extra strength. The trouble comes when you want to prove the design works. This is very typical. This is very tricky in the design phase, and typically the only instrument that's fast enough and accurate enough for this is a laser interferometer. But you can't really use this on the knife because it's moving, and it's quite difficult to aim at. We'll revisit this problem in a bit. So I'd like to discuss a few interesting features of our microtome, which have by no means invented by us, but there are aspects that we've worked on. I'd like to talk about the advanced oscillating knife that we use. We have an edge tracking camera for approaching the sample, and we have a fast piezomotor stage for additional movements. And then on a slight tangent, I also wanted to talk about some voxel printing of raw volume data, not necessarily EM data. So our oscillating knife, this is one of the things we've been working very hard on, because it's been known for a long time that having an oscillation reduces the cutting force. And so we've played extensively with control of this. And one thing that we found is no matter how carefully we make the knife holder, no two are exactly the same. So it's not a great idea to use fixed settings. And this is partly due to fine machining tolerances, but also considerations such as when you resharpen the diamond, it loses mass and things like this. So we control the lateral movement of the diamond with two piezoelectric actuators, which I'm indicating there. One of these expands and contracts to move the diamond back and forth, well, from side to side, and the other actuator gets compressed by the movement and generates a voltage in proportion to it. Our control system is able to read the lateral displacement of the diamond in real time and produce a waveform, which can be analyzed. And we've noticed a great amount of variability in this waveform, depending on the frequency, amplitude, and type of sample being cut. And when all is operating properly, the knife is making a very clean side-to-side movement. You typically get a sinusoidal waveform coming back. But when the knife is exciting other resonances or interacting with the sample in a strange way, you get a non-sinusoidal waveform. And here's an example of that. And just to illustrate the kind of differences, in this case, when we switched to 71 kilohertz oscillation, the sample went from being cut cleanly, each slice, to a real mess where the surface of the sample has just been stirred up by the knife in a quite a striking way. So there is variability, and we see that there's a lot of scope to experiment and play with different settings to get the optimum for each sample. So how much does it reduce the cutting force? It's hard to tell, but you can verify experimentally. So here's a video of about 20 images cutting through a squid skin at fairly thin slice thickness of 25 nanometers. And this is with the oscillator turned off. And what you can see is these pigment granules, which are in the chromatophore, are roughly spherical, and they're quite soft. And as the knife cuts more than halfway through, they easily get lifted out from the surface and carried away. So you can see them disappearing occasionally here. And as soon as you turn the oscillator on, the next 20 images, or so, you see that the knife is cleanly cutting all the way through them and not lifting out from the surface. So it's clear that there's a reasonably large reduction in cutting force from the oscillator, but I couldn't quantify it. So it can be quite difficult to verify by eye whether the cutting is uniform. I'll just play this video. So if you look at the raw backscattered image, can you tell that it's taking thick, thin cuts? Well, it's quite difficult typically, and the backscatter image is normally quite forgiving for this kind of thing. And yeah, so one way to do it is to calculate a stack of difference images. So each image subtracted from its neighbor. And when you plot this, which you can see with the lookup table here, it becomes very obvious whether the knife is doing thick, thin sections or it's alternating. We had a play around with quantifying this. You can actually generate a single metric to show the strength of this behavior, although this is only relevant if you're cutting through a sample where the structure and general shape and distribution of the sample doesn't change much through the stack. So brain would be a good example of this. You basically want to calculate a running correlation through the stack of a block of images, say 10 images, with another block shifted by 1. If you calculate the correlation of this, it gives you a measure of how much the images are alternating in thickness relative to each other. These are the difference images that we're looking at. And so just to compare a few of the scores that we've generated, with a good data set which shows no problems, then you get a low score around 0. With an artificial data set which has very deliberate alternating thick, thin images, then you'll get a high score of around 1. And the data set I showed previously has a score of around 0.7. So this is one of the rough calculations that we use when we're using the microtome and analyzing the data that comes back, just to see, it will tell you whether the cutting is starting to alternate thick, thin before you can see it by eye. Another thing that we've looked at is a knife edge tracking camera. So we have a series of mirrors on a mechanism which keeps the camera field of view centered on the edge of the knife. And this is a CCD camera, which you can see inside this black box. This is a CCD camera which is used for the approach to bring the sample to the knife. And this kind of setup overcomes the typical problems with low frame rate camera or blurring of a moving object as it goes across the screen, and lets you see very subtle clues that you wouldn't normally when the sample is very close to the knife, such as very tiny bits of dust being disturbed and things like this. I'll show a video which is sped up if I can. Okay, unfortunately that video is not playing, but it shows the knife skimming backwards and forwards and shaving material off of the sample while the knife edge remains completely fixed on the screen. So it's extremely easy to see even the tiniest touch on the sample. So a few interesting data sets that we've acquired with this setup. Because it's very portable and universal, we were able to pair it with an EDS system fairly easily. And this is something that needs further exploration for biological applications. I'll see if I can play the video. I'm not having much luck with the videos, unfortunately. The difficulty of this would be that the amount of elements need to be fairly low in the biological sample, and it still takes a high electron dose to detect them. So for something like this, you would tend to take an EDS image every 10 cuts because you do subject the sample to a very high dose. Ah, there we go. Yeah. This is maybe less relevant because this is aluminium, but just to show that it has a lot of different applications. Just want to show a few kind of pretty pictures of data sets that we've acquired. So this is a flatworm. This was a 1 week long acquisition. Squid skin chromatophore. And tubules in tooth. This was a 4-day acquisition. The final subject I'd like to talk about briefly is a bit of a pet project. I think it could be very useful for showcasing volume data and also for outreach purposes. And this allows you to visualize physically in the same way that you would do with a volume visualization on a computer. The kind of visualization before you do a segmentation, you just a volume visualization of the data. So voxel printing is currently used for high-end prototyping, but the firmware and software of these kind of printers is completely geared towards converting an object represented as a mesh or a surface into voxel form, as is standard in the industry. However, our volume data typically already exists in voxel form. So if only we can interface with the printer on a lower level. With the help from a company who owned one of these printers, we were able to do this. And we kind of came up with our own models and scripts in order to figure out how to combine the ink drops to produce the desired color and pattern. It took a bit of trial and error, but we got some nice outputs in the end. This procedure shown on the screen in not too much detail is just showing how you convert the raw data. You create a lookup table of it as if you were going to view it on the computer in a volume viewer. And through a few steps, you convert this into a series of dithered ink drops, which the printer is going to produce. And then you kind of go back and you verify that it looks roughly like what you were hoping it would look like. So, for example, one voxel in your raw data would be split into many subvoxels to produce the desired appearance. So yeah, that's it. So this is some raw data that was sent to the printer, just being visualized on the computer before it goes, and a couple of comparisons between a volume rendering on a computer and the resulting printout. The printing is extremely fine, so you can actually print things like spheres, and you need very, very minimal polishing afterwards. There's a few images of the most recent batch. The data set at the lower right actually consists of 4.9 billion individually printed voxels, which will be very tricky to do with beeswax. So thank you very much for your attention, and I look forward to taking questions in the time afterwards.